Okay, so I want to do something in this video. I don't know if I have to stem this off and do like a separate video, but I want to move our decompression code into a subroutine to make it more versatile. So right now our load level decompression only happens in setup. And that's not very useful to us if we want to load other screens and use them to kind of traverse into a game. So we can only ever write one screen with this method in setup, but let's take it out of setup and use it as a subroutine. So what code do we need to cut and paste? So let's instead call this load level 1 because it's in setup. Let's take all of this code out of setup and into a subroutine, and we'll call this load level because this is the versatile version of it. And at the end of it, since it is a subroutine, we have to return. And since we haven't called it in setup, let's do that. So jump to subroutine, load level. So this should stay the exact same. We've just moved it to a subroutine. Bam, the exact same. I also want to change one thing real quick. My mirroring is wrong for what I'm about to try to do. So I'm going to go to the INS header, change the mirroring to vertical mirroring. And that has made it to where the top left quadrant is our first name table at location 2000, and the second name table is going to be at 2400. Okay. Now, how do we use this subroutine over and over again? So what we did in setup was we initialized our pointers to our data. So we're going to have different locations of data with different screen data with screen information. So I'm going to name this level 1 because that's all it is. It's level 1. Let's rename this file down here. Instead of level data, it's called level 1. And let's add another one called level 2. And we'll call that level 2. So I actually do have both of these files. They exist. So this first level is the one with the whole bounding box scenario because we were checking collision. And this level 2 is that original screen that we were working with the kind of more wide open space. So these are the two screens that we want to kind of manipulate here in our demonstration. So let's say we want to load different screens to our opposite name table. We need a way to manage what name table we're writing to and what name table we're displaying on screen. So we need a variable in order to do that. So in load level, I'm going to load 0 and store it into a variable called NameTable. And this NameTable will only ever be 0 or it's going to be a 1. Now before I get into why that is, let's add this to RAM. Okay, now let's show why that is. So this NameTable variable has to either be 0 or 1, and that 1 has to be in the least significant bit because when we turn on our screen, when we write to this 2000 register and actually turn on our screen, we're also setting which name table to display. So we're setting the display name table, and that's this least significant bit right here. So if I toggle that to 1, we're going to load our level, but the NES is going to show us the second name table. So we've written all of our data, but this top quadrant is what the NES is showing us. So we can toggle this off, back to 0, and we're going to show the first name table. So now we can use that variable. So every time we turn on our screen, we incorporate this name table value before we write to 2000. So in order to do that, I'm going to use the OR operation. So we OR with our name table. And what does the OR operation say? So we're loading this hard-coded value, and then we're going to OR with either 0, 1, 2, 3, 4, 5, 6, 7, 8, or we're going to load this hard-coded value, and we're going to OR with 1. So let's work through both of these cases and see what's going to happen. So this first case, the OR operation says if either of the inputs are 1, you output a 1. So first one is a 1. None of the inputs are 1 here. None of the inputs are 1. Those are zeros. We have another case where there's an input of a 1, so we output a 1, and these are zeros. That's the OR operation. Now, what happens when the name table here is set to 0? Set to 1. This little 1 over here is going to be incorporated into this OR operation. So let's go through this again. We have a 1. We have a 0. We have a 0, 0. We have a 1. We have a 0. We have a 0. And we have a 1. So this OR name table has either created this hard-coded value, or it's going to change it to name table 1. Hope that made sense. And let's watch that in action. This is going to be left at 0. So we're displaying the first name table. Now let's set the name table to 1. Set the name table up here to 1. Bam, we're displaying the second name table. And we've written to the first name table. So now let's take care of which name table we're going to write to. We're going to use the same method with ORing with the name table, but we're going to run into sort of a issue. The name table addresses are either 2000 or they're 2400. If our value in our name table variable is only ever 0 or it's 1, if we OR the high byte of 20, with a 1, our output is going to be a 21. So we have to shift this bit over to the 4 position. And what does that look like? So let's say our name table is a 1, and we want to turn that into 24. So we have to move that to the 4 position in the bits. So we arithmetic shift left. Oops, this is a binary number. And that looks like this. We've shifted it to the left. We do that again, arithmetic shift left. 1, 2, 3, 4, 5. And it's now in the 4 position. So this equals 4. And then we OR with the value 20. And that looks like, let me cheat, 1 0 0 0 0. 1 0 0 0 0. So that looks like this. So now when we're ORing this 4 with a 20, what does the output say? The output says we have a 0, we have a 0, we have a 0, we have a 1, we have a 0, we have a 1, we have a 0, we have a 0. And this now equals 24. So at the end of this arithmetic shift left and OR operation, we could only ever have a 20 or a 24, which is exactly what we want. And I can't type today. 20 or 24. I hope that made sense. It's doing the exact same thing we did to the write on the register. So let's change that up here. So instead of this hard-coded 20, when we load level, we want to incorporate what name table we're writing to. So we load name table. We do that shift left twice to multiply by 4. And then we OR with 20. And that is setting either the high byte of 20 or 24 in this when we're telling the PPU what screen we want to write to. So let's see that in action. That should work. we're loading 0 into the name table, and we're going to then display the first name table. Bam. We wrote it, and we are in this top left quadrant, which is location 2000, the first name table number 0. Next, let's hard code this as a 1. So we want to write to NameTable 2, and we want to display NameTable 2 because of all these OR operations we added. Bam. We are now written into NameTable 2, and we're displaying NameTable 2. So this is the core mechanic that is necessary for being able to load different levels into the opposite name table and then viewing those on screen when they're done. Okay, I actually do want to stem this into another video. Next, we're going to write a routine that is set by like a trigger. Let's call this doorway a trigger, and we're going to load the next level when the character walks into this door, and we're going to use this setup of the subroutine to uncompress the second level data and switch to that other screen to actually view it.